Welcome to our lecture on the Cauchy distribution. Imagine you are blindfolded, spinning around, and firing a laser pointer at an infinitely long wall. Most marks land near you, but occasionally the laser fires almost parallel to the wall, landing miles away. Today, we will explore the mathematical rule that describes these wild, extreme outliers. Now that we have our laser pointer analogy, let us define what this distribution actually is. The Cauchy distribution is a continuous, symmetric, bell-shaped curve, much like the normal distribution. However, it has a unique feature known as heavy tails. This means the edges of the curve do not drop off to zero quickly. Because of these thick tails, the distribution constantly throws out massive outlier numbers that can ruin standard statistical calculations. It is defined by just two parameters, a location parameter for the center and a scale parameter for the width. To understand how these probabilities are distributed, we look at the probability density function. This formula gives us the height of the curve at any given point x. Notice that there is no exponential function here, which is exactly why the tails do not shrink fast. The symbol mu is our location parameter, shifting the curve left or right. The symbol gamma is our scale parameter, which must be greater than 0. As gamma increases, the curve becomes shorter and wider. This simple algebraic fraction is the engine behind those extreme outliers. While the previous formula gives the height, we often need to find the actual probability of our variable falling below a certain value. For that, we integrate the density function to get the cumulative distribution function. This formula uses the inverse tangent function, arctan. As x gets infinitely large, the arctan part approaches pi over 2, making the whole formula equal to 1, or 100% probability. This is incredibly useful because it lets us calculate probabilities directly without doing complex calculus every single time. Let us see this cumulative formula in action with a concrete example. Suppose a spinning radar emits a signal following a standard Cauchy distribution. We are given the location parameter, mu equals 0, and the scale parameter, gamma, equals 1. We want to find the probability that the signal hits the receiver line at a coordinate of 1 or less. Because we are looking for a less than or equal to probability, we write down our cumulative distribution function to begin. Continuing with our calculation, we carefully substitute our given numerical values into the formula. We replace the variable x with 1, mu with 0, and gamma with 1. The fraction inside the parentheses simplifies beautifully. 1 minus 0 is 1, and dividing by 1 just leaves us with 1. So we now need to evaluate the inverse tangent of 1. Now for the final steps. In trigonometry, the angle that gives a tangent of 1 is 45 degrees, or pi over 4 radians. We substitute pi over 4 into our equation. The pi in the numerator perfectly cancels the pi in the denominator, removing all irrational numbers. We are left adding 1/2 and 1/4, which gives 3/4, or 0.75. Physically, this means there is a highly likely 75% chance the radar signal will strike the line at a coordinate of 1 or lower. Having calculated a probability, we must now address the Cauchy distribution's most notorious reputation. It does not have a mean or a variance. If you try to calculate the average using calculus, the positive and negative halves of the integral both blow up to infinity. Since infinity minus infinity is undefined, the average simply does not exist. The moment-generating function also fails for the same reason. In the real world, if you keep taking samples, the average will never settle down. A single massive outlier will always come along and ruin it. To truly understand why the mean fails to exist, let us look at this visual comparison. The blue curve is the standard normal distribution. Notice how quickly it drops to 0 on the left and right, making extreme values nearly impossible. Now look at the red Cauchy curve. It stays lifted above the horizontal axis long after the normal curve has vanished. This visual gap represents the heavy tails we have been discussing. There is simply too much probability mass far away from the center, which is exactly what causes the mathematical average to blow up. Since the mean and variance are completely undefined, how do we describe the center of this distribution? We must rely on the median and the mode instead. Because the Cauchy distribution is perfectly symmetric, its highest peak, which is the mode, and its exact middle point, which is the median, both sit right at the location parameter mu. So if you need to find the center, you simply look at mu. This gives us a perfectly valid, mathematically sound way to describe the distribution without relying on a non-existent average. Let us apply this concept of the center to a fascinating property of normal variables. Suppose we have two independent standard normal variables, z1 and z2, both centered at 0. We define a new variable x as the ratio of z1 divided by z2. A fundamental theorem in probability tells us that dividing two independent standard normal variables creates a standard Cauchy random variable. Because it is standard, it inherits a location parameter mu of 0 and a scale parameter gamma of 1. Now that we have identified the distribution of our ratio, we need to find its median and mode. As we just learned, for any Cauchy distribution, both the median and the mode are exactly equal to the location parameter mu. We simply take our known value of mu, which is 0, and substitute it in. Therefore, the median is 0 and the mode is also 0. This makes intuitive sense. Since the original normal variables are centered around 0, their ratio is equally likely to be positive or negative, placing the exact middle at 0. You might wonder where this rebellious distribution actually shows up. It is incredibly important because it serves as the ultimate warning sign in statistics, proving that not all datasets obey the law of large numbers. In physics, it is known as the Lorentz profile, perfectly describing the resonance of harmonic oscillators and unstable subatomic particles. In finance, standard normal distributions severely underestimate the chances of catastrophic market crashes. The Cauchy distribution allows risk analysts to model these extreme, faraway events, acknowledging that massive outliers are sometimes a natural part of the system. To summarize our journey, the Cauchy distribution is a symmetric, bell-shaped curve famous for its extremely thick, heavy tails. Because these tails produce massive outliers so frequently, the distribution completely lacks a defined mean or variance. Instead, we rely on its location parameter to find the median and mode, and its scale parameter to understand its width. You have now mastered a crucial mathematical tool for modeling extreme, unpredictable events across physics, finance, and beyond. Thank you for watching.